Okay.
All right, we're back.
Yep. Can you share a screen?
Yep. Okay, I'm gonna play around with this and try and get this to go. Because I think if I share entire screen, I think that's worse. It's not going to be better, but I could be wrong.
Is there any way you can zoom it?
Hold on. Yeah. So this is on PyCharm. Okay. And I haven't been using PyCharm. I just started it today. I was using Emacs, and it's just been constant grief. So, so I'm jumping right now to PyCharm, and I have no idea where Zoom is on here.
Probably in the view.
Trying to get Spider going now.
Presentation mode. What's this?
Oh yeah.
Hey, wow, check that out. Man, it actually has a presentation mode. Okay. How good is this? Let's see. Is there a way to zoom even more?
I think we're good, more or less. We're gonna see if Austin can join as well.
I'm trying to get Slack right now.
Yeah, sure.
I just overhauled my computer, so I'm starting from scratch right now.
What? Oh, what a new system! You're redoing your system?
Yeah, I bought an SSD today and installed Linux on it, so I'm starting fresh.
Yeah.
New year, new me.
Oh yeah, 16 gigs of RAM now, solid state drive.
Yeah, pretty good. Pretty nice. What Linux are you using?
Mint.
Okay. I'm doing Manjaro, and so that's new for me.
Yeah, this is a new world for me. So I was on Windows 7 before.
Oh yeah, that's going to be different.
Yeah.
Windows 7. It's like 2 iterations back, eh?
Yeah, I didn't want Windows 10, man. I'm always hesitant when it keeps telling me to download this free, right? It's free, download. You know, nothing's free.
I'm actually pretty happy with Windows 10. I'm surprised myself. I remember Windows 8 rolled out. That was pain. That was bad.
Yeah.
But Windows 10, they got their act together, so it's okay.
Is there a way to download apps on way?
The Chrome?
I remember because I use a Mac at work. I'm still trying to learn that. Oh, I'll just download. I'll just go on the website. What's the workspace called?
Dlrl.
At Slack.
That's like that. Yeah, Slack.com. I don't think it's added. I think it's just dot Slack.
Yeah. Okay. I'm in.
Do you see the link?
Oh, Hangouts does not work in this browser.
Show me which browser you have. Firefox. Yeah.
It's funny. It worked on phone. Oh no, I was using my MacBook.
Just use my screen.
Yeah.
Yeah. Okay, Will. We're just gonna use my screen. We ready for you?
Yeah. Okay. No problem. All right. Yeah. This is Well, you can see this is not too difficult or brutal. This is inspired. Actually, I grabbed it from a guy. I have to admit it. I figured, just to save time. So I feel bad about that because I should have done it by myself. But I figured I was looking at it and I go, yeah, okay, I'll just grab this quick just to see if what runs, because I was having so many problems with things running. Anyways, that's my excuse. So the data, so that's going to come in as an array of arrays. And so he's just starting with the sequences. So that's the list here is the candidates, and then that's the score. So that's going to be its probability score. So for loop, so that's, okay, let me think if I remember this right. For each row of data, so that's one of the let me see if I remember this right. Yeah, that's right. So each row is a candidate. And so we are going to go through the sequence. So okay, initially it starts off, this is empty with 1 0. So it's going to build up over time. So you have seek and score coming from sequence.
Yeah, we could write this code a lot better. Already I could see problems with this.
Yeah. Well, it works. It works.
I'll rewrite it. Yeah.
So the first candidate, so yeah, for the length of row, so then we're going through the candidates that are in a single array. And what he's doing is he's adding, hold on, heck. Now I'm drawing a blank. How did this go? Anyways, for whatever reason, he did the log for the score. I'm not sure why that is. So that's...
It's probably to prevent arithmetic underflow. The probabilities are probably really small.
They are very small, yeah. Yeah, and so that makes sense because I noticed that, yeah, the probabilities were really small. This was for the calendar translation data that we were using. And so, oh man, I'm drawing a blank for some reason how this went. So yeah, the candidates are appended, all the candidates, and then that's sorted, and the key lambda tuple, so that's sorted by tuple 1 here, which is the score. And then from sequences, so that gets you the ordered list, and then the first K are put into sequences, and then the loop continues on through. So then that's the next, right? Okay, yeah, the first row is first iteration. Okay, there we go. It took me a while. TY. So we're starting at.
Can you copy paste that code? Sorry.
What's that?
Can you copy paste that code, put it in the Slack? I'm gonna just clean it up a little bit really fast.
Yeah, sure.
These like indexes like that are kind of frowned upon in Python. To make it more readable.
Oh yeah, which indices are we talking about here?
Well, for example, when it does like sequence score equals sequences I, and then for I in range length sequences, you can just write for sequence score in sequences. You don't have to index it every time, and then it gets slow because you're constantly like. It's not necessary. Like you see, you were at for I in range.
Yeah, right here.
You can just straight up write for sequence, comma, whatever the second part is, in sequences.
All right, for seek, comma, score in sequences.
Yeah.
Yeah, right.
It does pattern matching for you, right?
Yeah. Wait, aren't you supposed to use some term in order if you want to get both the index and the element?
So if it's like a list of tuples or an array of tuples, like in this case it is,
yeah,
it'll unpack it for you automatically.
Yeah, right. Yeah, right. It's going to get that right. So the row 0 is the first iteration, like the first word or the first output from the LSTM. That's what row is.
Okay.
Yeah. Okay. That took me a while. And so it's going through the candidates from, say, row 0. Yeah, that's where J comes in here. J is indexing through all the elements from the first row, getting all the candidates together, and then it gets building the candidates. Here, this is, okay, right, sequence plus J. Okay, yeah, there we go. It's summing. It's concatenating from the previous word, word at time 0 to word at time now wherever we are right now, and it's multiplying the two scores together. So the score so if we're on now the second, well, in our case they were symbols, the second symbol, you have to multiply the previous score from the previous time step, whatever that selection is, you have to multiply the two scores together, the two probabilities, and then you have to concatenate them as well. That's your candidate for this particular time sequence. Then you're appending the candidate tuple. There we go. Now it's coming back to me slowly but surely. Is this making sense, or do I need to try and elaborate on something here?
Okay, so what I see, just to make sure I understand correctly, the data is the whole output sentence, or is just the first output?
The data, actually, okay, this is where, and this is it's a great relief, because I thought I'm going to have to really dig into the guts and read all the Keras manual and do a bunch of hacking to try and figure out how to get beam search within the loop.
Mm-hmm.
And you don't have to do that. You have the entire encoder decoder finished completely, and what you do is you save the sequences. You save everything from the decoder, so you have all the outputs coming from the decoder, and that's your data. So you are not doing the search while you are looping through the decoder, which is a great relief. You don't need to do that.
Okay. Can you you don't have to do search as you do decoding?
Correct.
So everything is the data that you're iterating over, it's every single combination of a decoder?
Right. Yep. It goes through the whole thing, and you get, let's see if, so I don't know how familiar you are with this code or whether we want to go through it. I'll just come up a little bit.
Mm-hmm.
So here's the model. And we come down here is the for loop for the decoder.
So this is the one from the from drives, right? From Andrew for the.
Yeah, it's the. I'm not sure where I should point it out. So yeah, it was one of the. It's not Xiang's vanilla. It's but he derived his code from this one as well. It's the version, one of the version 4s, because there's 2 Coursera's that you repos that you put up.
Yeah.
So I don't know if you want me to try and dig out. Yeah. Okay. Yeah. It's one of those, and it's the version 4. And what I did is I stopped using Jupyter Notebook, because in the past I tried doing once a project with Jupyter Notebook, and I found that it got hugely, and it slowed you down. So I converted it just to a Py file. That's why I'm in PyCharm here with just a straight Py file.
Okay.
So yeah, you'll find it in there in the within the repo, what was it, sequence?
Mm-hmm.
Yeah, week 3, the week 3, one of those.
Okay.
Yeah. So this is the for loop for doing the decoder, done first. This is to get the context that we want to put in there for the attention layer. So this is one step attention. This is looping through every single output word. I'll call it an output word. That's why. So the loop is going ty number of times. So it's a context vector for each iteration. It does they're calling it the post-activation LSTM, but we know what that is. It's the decoder LSTM, one iteration. It gets the hidden state. The C, we ignore that. We just know that's the LSTM wants that for itself. We care about the S, which is the hidden state output. It goes through this output layer, which is a dense layer, where the softmax is the activation. That gives us out.
Mm-hmm.
Out is appended to outputs. So you're appending your results for that iteration for word 1. Then you go through the loop again for word 2, word 3, and every time you're appending the output to outputs. So can you see that pretty well? It's kind of like PyCharm just showed up, just the pop-up kind of like just gives you a hint of what it looks like. So that's it. You go through the entire decoder and finish it, and you're done. You're left. You've got an array of arrays with outputs. Then you can do the beam search outside of the loop.
Give me a second. I want to get the pen so I can draw it. Give me a second. How do I share my screen? Can you see my screen?
Yep, got it.
Okay, so I just want to make sure I understood it correctly. We have our encoder and decoder, right?
Yep.
And these are, forget, C and A.
Yeah, and C isn't shared between them, is it?
There was a context and then there was output, right? I'm gonna call it context, and then whatever I'm gonna call it output. I forget the terminology, right?
Well, let's call it C because we got the attention layer has its context vector.
Okay. Well, what's the other one then?
What's which?
Because LSTM outputs 2, right?
Yeah, at output C, and then the hidden. We call it. The convention we're using is A for the hidden output from the encoder.
Okay, so the idea is we got this, right? And then the outputs of these guys are fed, and then we are predicting some values, right?
Yeah.
All right. So we focusing on this part now, right? Your code, whatever you're showing, is this part, right?
Yeah.
All right, cool. So the question that I have is, as the output, right, for this decoder, we have some input, some prediction. That prediction goes back. That prediction goes back, and then we have these outputs, right? So what you're saying is, for every time it comes here, because the beam search was, are we using this word? Are we using this word? Right?
Yeah, I missed the part where it's like keeping track of which model it's using to predict the next word.
Because it seems like right now it does all of it, right? If that's the case, then the output should be this input for the next LSTM block should be our entire vocabulary, the entire dictionary.
Yeah, we need to, in the first step, you instantiate one model for the decoder. And on next step, based on which 2 words you picked, you have to have 2 copies of the first model and then test both of them with the 2 different words. And based on each step, you always keep just 2 models.
So the way I can I see it visually is, let's say this is our model, right? Let's say there are 3 boxes, right? 3 LSTMs. So we have the first one, and it outputs the probabilities, right?
Yeah, it's a softmax vector.
Yeah. So let's say this word and this word are the words, right, that we're interested in. I'm gonna paint them red. Like this is, and these are the words that we want to consider. So then what we have, when it comes to the second block, we kind of split. We send this word here, and we send this word here. and each one of them would output their set of probabilities.
That's what I thought too. I know what you're saying.
Yeah, call it.
Yeah, and it's
Copy the model.
because the thing is that feeding those outputs is intrinsically done with the recurrence nature of the LSTM.
Yeah, but
The
it seems like if the entire output is given, then we have, like, let's say the vocabulary size is n, then we have n versions of our model that we're running, right? And then it's going to be n to the power of the length, essentially, of our LSTM.
Yeah, right. Because if you were doing an exhaustive search.
Yeah, so that would be, yeah, I don't think our output is that large, because the whole reason we're doing Beam is so we don't have to explore all of it.
Exactly. Yeah.
Yeah, it's an exhaustive search through the search space is your output vocabulary, the softmax size of the softmax layer times t sub y, like you said, the length of the possible output.
But in this case, it's not times, it's to the power of it.
Or to right, yeah, to the power.
Our vocabulary, our dictionary is, let's say it's only 100 words, right?
Yeah.
We have 100 probabilities coming from our first LSTM decoder, right?
Yeah.
Then we're gonna have 100 of it coming for each one of these words. So it's time another 100. And if we have another decoder, then it's another times 100. So it's like, what, how many zeros?
I guess this only works because, like, we're not working with a huge vocab for this case. But, like, I don't think this is doing the
the beam search.
It's not doing it like how it was implemented in when we were talking about it for words and
Yeah.
sentences. Because, like, there has to be some sort of way where you have like a couple objects for your model to keep track of where you're at.
Can you try and expand on that?
Yeah, I'll draw something. Just touchscreen.
Yeah.
So on step 1, we're gonna get some sort of input vector from the encoder.
Mm-hmm.
Sorry.
It's not very convenient.
Not good
You
at
can
this.
draw this on the desk if you want to.
Oh yeah, that's
Under
better.
the camera. All right, we're gonna enable the camera now.
Yeah, okay.
Can you see it?
Yep, I think so. Okay.
This guy's gonna spit out some sort of vector, right? Or whatever we're gonna pass into the decoder model.
Yeah, that's the A.
Call this guy. So in step 1, this is gonna output a softmax based on whatever encoded information from whatever input sentence we gave it. You can almost say, like, going into the model xn, some sort of sequence of sentences, pumps through encoder, you get this vector. Decoder spits out a softmax of a bunch of words, blah, 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 blah. You pick 2 of them. Now, in this case, is when you have to kind of manage the models. Essentially, you take this model, you have to make 2 copies of it, here and here. And now, in this version of the model, you test this word as the input. In this version of the model, you test this word as the input. And then this goes on and on. But then here, when you have another 2 set of softmaxes, but again, we're only going to select the top 2. If the 2 are in here, on the next iteration, we copy this guy. Then we have 2 instances of this object. And then we continue. And we forget about this one, because this start word doesn't matter anymore. It's gone. See what I'm saying?
Yeah, and I think we're thinking. I'm pretty sure we're on the same page. And it's not models. It's the same model. It's the next iteration of the LSTM. But now that the understanding is the next iteration of the LSTM, you had to instantiate 2 separate LSTMs with now different inputs, right? like word 1, word 2, like what you have in the diagram. Say we'll call it that. But in fact, that this branching, it's actually accounted for with the LSTM's recurrence. It's hidden state. It's giving the entire output of the different numbers. It's assigning different values for the possible first word, and that entire vector goes in to the LSTM for the second iteration. It's getting that as the input. And then it's generating the now vector for time t2.
I see what you're saying. So this is a different.
I'm not following. Can you explain?
That hidden
Different than the machine translation model that I'm thinking of.
Yeah, because the softmax returns, or I won't even say softmax. I'll just say the result of the LSTM at time 2, it's already got the input of all the possible possibilities for time 1. It already gets that as an input, and it's already making its assessment of the probabilities for time 2 based on all of these time 1 words, I guess we'll call it.
So now, what's the point of the beam search in that case? That's why I don't get it now.
Because if you get the result, so at the end of it, at the end of doing the decoder, you've got a list of vectors that are, the number of vectors are the length of t sub y, our output length, and each vector is of size, what's it called, vocabulary. So you've got this big array of numbers, or tensor. You got this big tensor of numbers. You've still got an explosive, an exponential search space with the results, because you have to select for vector 1, you have to select one of those numbers. Vector 2, you have to select one of those numbers. And the thing is, they're not independent selection. In vector 2, whatever number you select, you have to compute by the multiplication, because it's word 1 probability times word 2 probability. And then so you got to find this path through this tensor anyways. So that's why you have to still do a beam search to try and avoid an exponential search space.
Yeah,
I think you still can't do, hold on, I'm not sure if I'm explaining right. You still can't do a greedy search with the resultant tensor. It's still going to be costly anyways. So I mean, it's see how to explain that. Basically, what you're talking about, all this branching off, is already in there in that tensor. That's the end result. I'm pretty sure this is the case.
I remember in Andrew N's video, he explicitly talked about this, and when he was talking about the beam search.
Oh, really?
Yeah, like I'm really remembering that paper where the inputs to the model each time were another token. Like it was an embedded token that's going into the model in each step. I think the date one is like just kind of totally different. That's what's causing the confusion.
All right, hold on. I'm going to look here on YouTube and see if I can see his thing, because maybe then I don't know. Earlier this afternoon, or this morning, I was thinking through it, and then it hit. Yeah, no, this is the maybe it was just wishful thinking then on my part.
Right, because so in this first step, right, this probability vector, it's P of Y first estimate given xn, right? Or at least the transformed version of xn. And then in the next step, this guy here is going to be, well, based on our selections, EY2. Sorry, it's not it's a given. Given our original input xn, and then whatever selection we chose. So like word 1. And over here, this guy is the probability of y2.
Yeah.
xn, and then word 2. And then each step, we have to kind of like maintain a state of like, what are we actually comparing it with, word 1 or word 2? And this chain just grows.
Yeah. Yeah. I got, yes. And now is that properly covered by the LSTM, by its recurrence? Because I believe it is, because it's taking those priors as input.
But it takes one prior, right? It doesn't take like.
From what I remember, like when it was explained, like these are inputs. Like this is the first input. It's an actual like embedded sentence. Then the next input is an embedded word, like whatever the decoder first generated. And then it goes on and on and on. You keep feeding a word in, you get another word, another word.
Yeah, I know what you're saying, because there should be, for the second time step, right, there should be a separate vector for each word. Hold on here. Hold on. Yeah, maybe it was wishful thinking. I saw that there's a recurrence and I thought, hey, it's accounting for it.
Yeah. And this guy here gives us constant memory, right? Because we only ever have to deal with 2 times n probabilities.
Yeah, or
the memory associated with the models.
Yeah, or k different models, right? Or k different paths through the LSTM.
Yeah.
Because that's the beam search parameters k. Yeah, maybe I screwed up here then. I was just hoping for an easy win.
Yeah.
Yeah, because then you got to dig into this for loop, and you got to stick in another for loop.
What would be the approach for us if we want to keep
the algorithm for this?
Yeah, implement this algorithm.
So essentially, write it like a pseudocode. We're gonna def beam search. Let's make it a function. I guess what you'd want to do as an input, well, it depends how you structure it, but essentially it's going to need some sort of model. So decoder will some LSTM thing.
Mm-hmm.
And then it's going to need XN, like our initial embedded sentence. And in this case, this model is like a callable, like you call the model with some sort of input, and it'll output whatever the next it'll output the probability vector. You say P equals decoder xn. This is the initial P. And then we need our parameter size, right? So from here, beam is 2, and we're going to take candidates will be P, and then all sorted P. Okay. It's already becoming a mess. So we'll take the top 2 out of this sorted list, or the N2, whichever way you sorted it. And then this is going to iterate. Now, because we have a thing of 2, now we actually need 2 separate models. So then, I'm not sure how you code it.
I think you should be passing LSTM to this function.
Yeah, probably.
Yeah, on the code, it would be an outer loop, because you're going to instantiate not a model. You're instantiating a separate, distinct iteration through the LSTM
Yeah.
with k different inputs. But hold on, I'm thinking about this because I'm not sure whether right, because say for time 2, you've got that vector, and say for word 1 in time 2, it's got only a single number. Well, see, now we got to look back at the LSTM. How is it determining that value?
Which values, right?
If it's coming out with a single, so time 2, word 1, it's got one number associated with it in the hidden state. If I remember hidden state right.
Yeah. And for this, actually, you probably want to define as a recursive function, actually.
Hold on a sec here. Because if it does, I already forgot then how LSTM determines that. What number that is. Do you remember that?
Sorry, like, what do you?
I'm just trying to remember if now this is right. Like when you're saying when we're selecting word 1 or word 2 from time 1,
Yeah.
and what are we changing with the output? What's different? So you want to select word 1.
Right.
So then what does that mean? What's your vector then that you're sending to the LSTM next round?
It's going to be some sort of like word embedding.
I think what you're asking is the context and the hidden state, right? Can you see me?
Yeah, well, the context is the context. That one doesn't change. That's the attention layer doing that. Oh, you mean the C?
Context is different. So we have C and we have hidden layer, right? And then we usually have the input, right?
Well, in this case, it's only the hidden is the input, if I understand right. I don't see it anywhere in here that there is another input.
Right. Yeah, I think we're just kind of like trying to describe two different things. I think that's what's happening. So
anyway, so we're passing the context, hidden state, and the output of the previous one, right? So for the next layer, this guy would be the input, and these two just flow as the.
Yeah, that what you're talking about, the Y hat. I don't think in this case it's being used. I haven't. Can you see that somewhere in the code where it's actually being used?
yeah, I don't remember if it gets used in that the time, the human time to or a human date to machine date model.
Yeah, right.
That one as clearly as I do the other paper.
Oh, did you see it? It was used in another one?
Yeah, because like the thing I'm trying to describe here was more the case for that first paper we were looking at. Where it was just translating the French to English or English to French.
Mm. And they were using Y hat. Okay, well, Y hat is not a big deal. If I understand right, Y hat is basically a softmax on H out.
Oh,
I remember.
right. I think this H, like it goes through some like operation, but then it's being copied. So you can say that H is this same thing essentially. H is the Y. So we can ignore.
Well, Y could actually be like an actual like the selection mechanism, right?
Yeah, this is the word that we get out that you have above. But this word, this Y
It's based on
H are the same.
softmax. Yeah.
Yeah, well, the Y hat is usually what's coming out is a softmax vector.
Yeah. So
And that,
say that.
But it has to be like it has to be transformed before it goes back into the model because the model is expecting like an embedding, right? Like it needs a token, it needs like a seed. Like if you, it's almost like you imagine like sampling these models. Like you wouldn't like initially give it a probability distribution. You'd give it a word. and then see what it generates from there as like a seed.
Yeah, that's for the encode. My understanding, that's for the encoder. The encoder is taking in words.
In the end of the day, once you have like a model trained, you can just like you can sample it like any old distribution based on like whatever you want to start with.
Yeah. Okay. Well, for me, when I'm using the word model, the model includes both the encoder and decoder that are fused together, and I would call that the model, the whole thing together.
But you can sample from the decoder because like it needs to work like the outputs have to be like the actual tokens because it needs to know based on the token it got before what to generate next. Like I think the way Eric's describing it, it's almost like the beam search gets like built right in, where every y is that whole vector, and then goes into the other one. The problem with this is that like doesn't it blow up once you have like a vocabulary of 80,000? That's right. I get like kind of lost. Like I don't see how it scales that way.
What do you mean exactly blowing up? So you're saying you get a large output vector?
Yeah, if this is a softmax at every step, like if it's always a softmax being fed into this.
Yeah.
Then if you have a vocab of 80,000, which was it was 80,000 and 140,000, I think, for the French to English one.
Yeah.
Like, yeah, it's a massive vector, right?
Yeah, it's a big vector, but and that's the input to the next round in the LSTM, the next iteration. So it's constant. It's just it's outputting a same large vector, and it's accepting as input the same large vector. It's not changing in size.
You know what's happening with this y? This h is usually the vector, right? With probabilities, and then it goes through softmax, and then this thing is y. When we pick one word.
Yeah.
So this h is still a vector of probabilities.
Yeah. That's what I think. Yeah. Well, sorry.
So how do we
that h won't be because that'll be just the activation. It has to go through the softmax to become the probabilities.
It has to know probabilities.
The softmax isn't built into the model, so h is separate.
So what is h?
Activation.
I see. So what you're saying is this thing goes from this LSTM block, it goes here.
It essentially conveys the same information. The softmax just makes it a probability distribution. So it sums to one, right? But the information contained is essentially the same.
Yeah. So what you're saying is we take this thing out.
Yeah, the difference between y hat and h is not much. It's just one up. Except
we take this word.
There's a dense in here.
The vector, and then we pass this guy here, right? And we have two of those, like the first option and the second one. So we have like y1, and we have, let's say, y2, which is the second probability. We convert it back to embedding, then we pass it to an XLSTM.
Or you know what? So you know how this probably works? The input can be like a word embedding. The output can be a like a whatever probability distribution, but we don't necessarily have to make that direct link. Like basically you run the decoder with any kind of input vector, it spits out a probability distribution. Then you just, based on a probability distribution, you pick your next input vector. Right? It's not necessarily a direct connection. I think that's where we're getting caught up.
Yeah, let's try to search.
I'm gonna find the video, the paper.
And let's search the code. Maybe someone implemented this thing already. We don't really need to.
Yeah, hold on here. Figure out. To implement in Python.
that mini series. There it is.
It's almost like you know that the 1,000 choices, then that's what research would be.
Such let's go.
So notice one thing. If beam search decides that the three most likely and so beam search will then investigate the top three possibilities.
Research Keras.
And the outcome of this process hopefully will be that at one word at a time, the research will decide that sentence that this is the likely sentence. And we see more details of this result. Exercise is all with it. So what we look at
This increased performance.
possibilities. Notice that the movement was set to be one, so it's zone one. Then this essentially becomes the new research algorithm. But by considering multiple possibilities, some number at the same time, research will usually find a much better output sentence. We've now seen how research works. It turns out there's some additional tips and tricks and requirements that help you make research work better. So, this parameter of B,
By scoring by multiplying.
example, set U with B. And what this means is research will consider not just one possibility, we consider three at a time. So in particular, let's say evaluating this probability over
Yeah, that's right. There's the natural logarithm.
finds that the choices in J September are the most likely three possibilities for the first word in each output. Then research will store away the memory that it wants to try out all three. And if the beam parameter was set differently, if the beam parameter was set 10, then we keep track of not just 3, but 10 most likely possible choices of the first.
So that's the thing. It keeps track of choices. Like that's where I'm. There's no need to keep track of choices if you're passing like the entire vector the whole time.
So to be clear, in order to perform this first step of beam search, what you need to do is run the type sentence through this decoder network, and then this first step of the decoder network, this is a softmax output of all 10,000 possibilities. Then you take those 10,000 possible outputs and keep in memory which were the top three. Let's go on to the second step of beam search. Having picked in Jane and September as the three most likely choices for the first word, what beam search will do now is for each of these three choices, consider what should be the second word. So after maybe the second word is A, or maybe it's Arab, just listing words in the vocabulary dictionary, or somewhere down the list, maybe September, somewhere down the list, visit, all the way to C. So to evaluate the probability of the second word, they will use this neural network fragment as the decoder. And for the decoder portion, when trying to decide what comes after in, remember the decoder first outputs y at 1. So let's set this y hat 1 to the word in. Keep this back in. Because we decided for now that
Yeah. The way Andrew explains it is it's feeding words. Now, are you just doing that for simplification, or?
Okay, there's if it we've got the same thing. He's got a a beam search and a refining beam search video. Which one are you watching?
The first beam search.
Okay.
This video,
Yeah, do you want to share it?
Can you post it on Slack and I'll share it?
Yeah. Well, I got the video on. I can share it. I figure we may as well look at the same thing if we're looking at it.
Yeah, let's do it.
Yeah, hold on here. Okay, come on. Am I sharing it?
Yeah, but it's half screen.
last video, do you remember?
Hold on. What is it? Full screen mode? Now I can't see what I'm doing. Does this look right?
Yes.
Okay.
If you go to like 2 minutes and 30 or so.
2:30. All right.
Or go a bit earlier than that, I guess. It's when he starts the algorithm.
Last video, do you remember?
Oh, that's too far back.
First thing you search is two.
Can you turn up the volume a bit?
Here are lists
Hold on. I'm on max here.
of 1,000 words.
How is that?
Use headphones.
Yeah, I'm using headphones.
Okay.
But I mean, I don't know that that'll make a difference if I don't use headphones. Well, all right.
And to simplify
Do you want to share it instead?
Sure. Can you post this video on the GitHub? I mean, Slack.
That's it. Yeah. Because I can always hear from you guys. Well, never an issue.
Or we hit play at the same time or something.
this video,
Yeah. They sync it up.
All right. So let me share my screen.
try to
Can you see it well?
Yep.
Might as well just watch from the beginning.
in the last video, you remember how for
How about the volume? Is good?
Good.
machine translation, given an input French sentence, you don't want to output a random English translation. You want to output the best, the most likely English translation. The same is also true for speech recognition, where given an input audio clip, you don't want to output a random text transcript of that audio. You want to output the best, maybe the most likely text transcript. Beam search is the most widely used algorithm to do this, and in this video, you see how to get beam search to work for yourself. Let's describe beam search using our running example of the French sentence Jane visite l'Afrique en septembre, hopefully being translated into Jane visits Africa in September. The first thing beam search has to do is try to pick the first words of the English translation that's going to output. So here I've listed all, say, 10,000 words in the vocabulary. And to simplify the problem a bit, I'm going to ignore capitalization. So I'm just listing all the words in lowercase. So in the first step of beam search, I'll use this network fragment with the encoder shown in green and the decoder shown in purple to try to evaluate what is the probability.
There's like
of
one
that
thing here I was
first
just
word.
thinking. So the initial input to this network can't be a probability distribution because the encoder gives you some sort of embedding, right?
Yeah, that's the encoder part. The encoder part is understood that does its job and it's done.
Right.
And then now we're talking about exclusively the decoder part.
Yeah, but the initial input comes from the encoder, right?
Yeah, that's the A primarily, maybe C as well if it's an LSTM. But like if we're just using a regular RNN, it's just the last A.
But you know what I mean? Like the initial input is not a softmax from the encoder.
It's 0.
No, it has.
No, it may not be a softmax, but it's some vector.
Yeah, but it doesn't make sense that the input is always some vector, not a probability distribution, because in this case we have a different input then. The first input is one thing and then the rest of the inputs are something else.
All right. So LSTM takes 2 as input, right? C and hidden state. Which one are you talking about?
Just like the video.
But this one just only has like 1 line. Our model is LSTM. So are you talking about the C or H?
But there's going to be, I guess, like whatever it's going to get is some concatenation. And whatever the encoder spits out, it's going to be it's going to go into X actually. These guys are going to be initialized, I think, to 0, but X is what's going to come from the encoder.
Yeah, I don't know if X is used in this case for the language translation.
That's what I mean. It's gonna be either 0, so it's just gonna be whatever the last LSTM will spit out.
Yeah. Where did we, because this is,
Because he's naming this X, right? This X is getting built by the encoder, and it's like the seed for the decoder. Like, I don't know if it's being passed implicitly through activation. I think it's actual like embedding.
the X's in what's on the screen right now. That's the inputs.
Yeah, but it's building like it's trying to build some sort of encoded sentence.
Right.
I don't think
Representation of
it's
the whole thing, right?
yeah, I don't think it's like being passed through the activation. It's like building something, a vector.
Yeah. Okay. Yeah. So like the final time step, the LSTM cell. I mean, it's got the last time it does its round. It's whatever its output is, whatever that hidden state, maybe a Y hat. The C goes out as well, and then but that's it. That's what the decoder or the encoder LSTM. That's all it does. So those are the only options we've got. Yeah, there's H. The C thing we should just ignore. That's confusion, right? That's LSTM doing its own bookkeeping thing.
Wait. I don't think we should ignore C. What C stands for again? This is the memory, right? This is actually what encodes everything.
Yeah, that's the short-term memory trick. The C. I'm just saying we can ignore it simply because it's not doesn't involve what we're working on or the issue we're dealing with. That's like C is for handling the gates, the forget gate, the on gates, all these different gatings.
C is a cell state, right?
Yeah, I guess for the gating, it is.
Yeah, I think C is used to actually encode that thing. C is the one that encodes, if not all, but portion of whatever the input sentence was. That cell state, I think that thing is important.
Yeah, it is. Sure.
But I'm not sure if we are passing just that. So C, I think C is connected to the decoder. Sequence. Yeah, so C keeps going, right?
You know, I would think that's A. Well, that's one arrow, which it doesn't say. I think you got the option whether you want to have C continue or not. I don't think the option is the hidden state. That one you do need to go from the encoder to the decoder.
Yeah, so C is being passed. Okay, so the output is the hidden state. This is what we're passing. So C is being passed to decoder and H is being passed. But in this case, our start is zeros. H is being inputted, and then the output, yeah.
The output are tokens.
Yeah.
Okay.
It is.
It's a
C and H and all of it.
Yeah, in this case, I've seen different ones where that yes, we can. Those outputs are not being moved forward.
So the embedding is done based on the activation and memory layer. That gets passed through directly. But then each step of the encoder is fed some sort of word embedding based on this. And this is the idea that they had in that paper as well, where it's like passing words.
Yeah, okay. I'm focusing on all right. My attention was on the translation for the calendar. So because when you're saying word embedding, yeah. Okay, sorry. What were you just saying there? The word that's more involved. Okay, hold on. Yeah, all right.
The one with attention?
Hold on. Which Let's get that paper.
I'll post it again.
Yeah, I'm getting it coming up here. What was the name of it?
Sequence learning with neural networks.
All right. Where's R? There it is.
Does it use LSTM or GRE?
LSTM.
No, I think you do need to send it up. I don't have.
Yeah, I'll just post a link. I got it.
Huh.
Just direct message you. Money in the channel.
I'll
So what's the
continue.
probability of the first output y given the input sentence x given the French input? So whereas greedy search will pick only the one most likely word and move on, beam search instead can consider multiple alternatives. So the beam search algorithm has a parameter called b, which is called the beam width. And for this example, I'm going to set the beam width to be equal to 3. And what this means is beam search will consider not just one possibility, but consider 3 at a time. So in particular, let's say evaluating this probability over different choices of the first word, it finds that the choices in, Jane, and September are the most likely 3 possibilities for the first word in the English output. Then beam search will store away in computer memory that it wants to try out all 3 of these words. And if the beam width parameter was set differently, if the beam width parameter was set 10, then it would keep track of not just 3, but of the 10 most likely possible choices for the first word. So to be clear, in order to perform this first step of beam search, what you need to do is run the input French sentence through this encoder network. And then this first step of the decoder network, if this is a softmax output over all 10,000 possibilities, then you would take those 10,000 possible outputs and keep in memory which were the top 3. Let's go on to the second step of beam search. Having picked in, Jane, and September as the 3 most likely choices of the first word, what beam search will do now is, for each of these 3 choices, consider what should be the second word. So after in, maybe the second word is A, or maybe it's Aaron. I'm just listing words from the vocabulary from the dictionary. Or somewhere down the list will be September. Somewhere down the list is visit, and then all the way to Z. Maybe the last one is Zulu. So to evaluate the probability of the second word, it will use this neural network fragment where there's the encoder in green. And for the decoder portion, when trying to decide what comes after in, remember the decoder first outputs y hat 1. So we're going to set this y hat 1 to the word in and feed this back in. So this is the word in, because we decided for now that because we're trying to figure out that the first word was in, what is the second word? And then this will output, yes, y hat 2. And so by hardwiring y hat 1 here, really the input here, to be the first word in, this network fragment can be used to evaluate what is the probability of the second word given the input French sentence and that the first word of the translation has been the word in. Now notice that what we ultimately care about in this second step of beam search is to find the pair of the first and second words that is most likely. So not just the second word that's most likely, but the pair of the first and second words that are most likely. And by the rules of conditional probability, this can be expressed as P of first word times P of probability of the second word, right, which you are getting from this neural network fragment. And so if for each of the 3 words you've chosen, in, Jane, and September, you save away this probability, then you can multiply them by this second probability to get the probability of the first and second words. So now you've seen how, if the first word was in, how you can evaluate the probability of the second word. Now, if the first word was Jane, you do the same thing. The sentence could be Jane A, Jane Aaron, and so on, down to Jane is, Jane visits, and so on, And you would use this neural network fragment. Let me draw this in as well, where here you would hardwire y hat 1 to be Jane. And so with the first word y1 hat hardwired as Jane, then this neural network fragment can tell you what's the probability of the second word given the input x and given that the first word is Jane. And then same as above, you can multiply with p of y1 to get the probability of y1 and y2 for each of these 10,000 different possible choices for the second word. And then finally, you do the same thing for September. All the words from A down to Zulu, and use this network fragment. I just draw this in as well to see if the first word was September, what are the most likely options for the second word. So for this second step of beam search, because we're continuing to use a beam width of 3, and because there are 10,000 words in the vocabulary, you'd end up considering 3 times 10,000 or 30,000 possibilities, because there are 10,000 here, 10,000 here, 10,000 here. So it's a beam width times the number of words in the vocabulary. And what you do is you evaluate all of these 30,000 options according to the probability of the first and second words, and then pick the top 3. So we're going to cut down these 30,000 possibilities down to 3 again, down to the beam width.
It's a key detail like we did.
And so let's say that of these 30,000 choices, the most likely were in September, and say Jane is, and
best pair is not the best
Jane visits. Sorry, this is a bit messy, but if those are the most likely 3 out of the 30,000 choices, then that's what beam search would memorize away and take on to the next step of beam search. So notice one thing. If beam search decides that the 3 most likely choices for the first and second words are in September, or Jane is, or Jane visits, then what that means is that it is now rejecting September as a candidate for the first word of the output English translation. So we're now down to 2 possibilities for the first word, but we still have a beam width of 3 keeping track of 3 choices for pairs of y1, y2. Before going on to the third step of beam search, just want to notice that because the beam width is equal to 3, at every step you instantiate 3 copies of the network to evaluate these partial sentence fragments in the output. And it's because the beam width is equal to 3 that you have 3 copies of the network with different choices for the first word. But these 3 copies of the network can be very efficiently used to evaluate all 30,000 options for the second word. So just don't instantiate 30,000 copies of the network. You need only 3 copies of the network to very quickly evaluate all 10,000 possible outputs at that softmax output, say, for Y2. Let's just quickly illustrate one more step of beam search. So we said that the most likely choices for the first 2 words were in September, Jane is, and Jane visits. And for each of these pairs of words, we should have saved away in computer memory the probability of Y1 and Y2 given the input X, given the French sentence X. So similar to before, we now want to consider what is the third word. So is it in September A, in September Aaron, all the way down to is in September Zulu. And to evaluate possible choices for the third word, you use this network fragment where you hardwire the first word here to be in, the second word to be September. And so this network fragment allows you to evaluate what's the probability of the third word given the input French sentence X and given that the first 2 words
it's confusing the way he puts it. Because in this case, it looks like the outputs are words. In this case, the outputs are vectors. But when he says you hardwires, it's like this output isn't necessarily the same as what's going into the next one.
Yeah, I assume they're not words that are outputs. They're still, well, they could just be one hots, but Well, no, what's output is the softmax. But yeah, when you make the selection from the softmax, I'm assuming you're not translating, or I mean, you're just giving off the.
Well, yeah, what I mean by word, just like in the sense, like the input to the model has to be some sort of vector, but it's not the whole probability distribution. Like it's like input a word, output is a probability distribution. Select a word and like recycle.
Right.
Yeah, and selecting word is like whatever is the proper representation for the. Yeah, we're back to okay. So that was this morning. I just had probably just wishful thinking. Then that we can do it. Well, then the loop has to be in that for the for loop. Then where the attention is being done. That's where.
Do we make copies of the decoder? Because to me, it seems like you take a decoder like as a separate network, make copies of it, but how can you hardwire those first two inputs and get the third output? How can you encode like hardwire first three inputs and get the fourth output? You gotta iterate, right?
Yeah, so every time you run the model, it's going to save some sort of internal state. And that internal state will encapsulate like chosen words. Like give this model, give it a word, it'll update its internal state. This version of the model will give it a different word, it'll update its internal state, and now it's gonna have a different state. This one will have a different one.
Right, I get that part, but how do you say, give me the output of the second LSTM, given this word for the first LSTM, and then just take that? It's more of like a programming part.
Yeah.
It's not so much of a conceptual one.
Yeah, what is the representation? Is it one hot usually when we're saying?
In the paper I linked, it's word embeddings.
So
really
it
depends on how you encode the thing yourself.
Okay, right. Okay, we got the option, one or the other.
Yeah, for the calendar one hot's fine because like I guess the vocab's not huge.
Yeah.
But for the language translation, and then the one hot, you don't really get like any meaning, right? So they found just with the translating language, the embeddings kind of capture some sort of meaning, where then two similar words end up with like a similar vector, like a small cosine difference.
Okay. If I remember right, hold on. If for word embeddings, isn't the output the y hat, isn't that an index, just integer?
For what?
And that isn't the output an integer to a word embedding vector? Like, so the word embedding is like a large matrix.
Yeah.
So usually, if I understood you right, word embedding usually means a particular vector in that matrix, like a column or a row that represents that word. Is that what you're referring to?
Yeah, like it'll like when you choose a word in this case, you'd essentially choose integer.
Yes.
The integer maps to some vector.
Yeah, and so if it's the softmax output from the decoder, that y hat, what it is that each index value of that softmax vector is also corresponds to the index value for a particular word. So yeah, the 10,000, if you have 100,000 vocabulary, your softmax is a 100,000 sized vector, and each word is represented by one index point in that softmax vector. So you're picking the one with the highest probability usually. And that's so that's your index number. So are you inputting the index number or the word vector?
No, you take that word, convert it, make an embedded vector out of it, and then input that. So essentially, how you trained your network, that's how you use it. So if you train your encoder and decoder with one hot encoding, you can do that. It will learn that way. But then when you do beam search, then you have to when you do beam search, then you have to input in the same format those words. If you use one hot encoding to train your decoder, then you have to input one hot encoder of your word when you do beam search. I don't think beam search is used when we do the training, right?
No.
Yeah, it's only used when you're querying.
Yeah, I think that gets cleared up in the
Okay.
in the
Okay.
next video.
Okay.
Yeah, that makes sense. It doesn't. It's why would you use it in the training?
In our case, it's going to be like several steps. Each LSTM outputs the probability vector of, let's say, 10,000, right? In this case, and that 10,000 essentially is a dictionary. We take the maximum one, and let's say it's like, I don't know, number 4. Let's say it's somewhere like iron, right? So we take that word and then we run it through our word embedding mapper, or like whatever we call it, and then we get, let's say, representation, one hot encoding, we get like word embedding of.
Well, see, the decoder. Okay, we got to look at different code then. So yeah, because I'm only thinking the one kind of the code base. The decoder, what is it getting for? We're back to that again because I don't know that the decoder.
What is it getting?
Have you seen code where the decoder or some clear, very clear diagram where it's the decoder is getting a word embedding vector as opposed to a vector with a bunch of that represent a bunch of indices to word embedding vectors?
All right, so I think you let me maybe share the. Let me draw something.
Yeah, because I don't remember any of the other examples we saw. If you want, yeah, okay, go ahead.
All right, so we just talk about the decoder, right? So let's say these are two LSTMs, right? And we just got the cell and the hidden states, right? We're gonna be passing them. We're not gonna look at them yet. So for the very first word, it's gonna be zeros. Like we don't care about it. We don't
Start
have
token
anything.
or something.
Yeah. Now this guy goes, does its own thing, and then the outcomes, the probabilities, right? This is the vector of probabilities.
Yeah.
Now we pass it through softmax. Oh, after we pass it, that's what we get, right?
Yeah.
Anyway, so we get
Yeah.
the probabilities, and
That's right.
say this is the word that we're picking, right? And this is word, let's say iron. This is something that humans can use. We're gonna append it to our results, for example. I don't know how you're gonna do that. But then we do the word to vec again. We pass it through another filter, and then this is fed here. It could be word to vec or one hot encoding or whatever you want to, depending on how you train this thing to begin with. And then it goes back again. You get some results, the probabilities. You take a word out of it, like I don't know, some word. Then you make a vector out of it again, and then you pass this thing into it. Okay, so let's go. Now my question is, how do you, when you query this thing, right, in Keras or Tensor or whatever, how do you say, okay, here's my model. I'm assuming our decoder is going to be the same. It's trained already, so we have it. So once you have that, how do you say, okay, only give me results for this, from the second LSTM, given these two initial inputs? If we can do that, then the function is very simple. For the beam search, is going to be, input is going to be word, or like a vector of words, right? One or two, whatever it is, and then the model.
Well, I think no, how it would work is because this is happening in like T1, T0. This is the same model, but now at T1,
Yeah, it's the same model, yeah.
right? All that's changed is its internal state.
Yeah.
So in the first step, you have a decoder, and then you feed it like a
Encoder. Is that what you're talking about? The first?
just a decoder.
It's a decoder.
Okay. All right.
So it gets like its word, which in this case is going to be just zero, like a start word, and it gets whatever the input is from the encoder. In this case, like a concatenation of these guys.
Okay.
So this is our first model. Like we'll say results one equals this, and this result one is going to end up being like Aaron, the initial word. So then we can just say in step 2, we can say like on our R2, like our first candidate equal R1, our second candidate equal to R1. So we just made 2 copies of this network here.
Mm-hmm.
And now we're just going to try our 2 words. So in this case, we'll feed it Aaron. Or we spell Aaron. And whatever. Well, it already has some sort of internal state, right?
Okay, so what is the DEC? Is it a function or is it a class?
It's a callable object is the way I'm seeing how it's going to run.
So it's a class, right?
Yeah.
Okay, so
You can either like do like you can make it callable or you can like do d dot like run like call a method on it. It depends how you want to implement it. Yeah. It's more explicit if you do it this way. Don't make it callable. Just say like model dot run like or test or whatever you want to name it. And then when it runs another word, it's going to update its internal state.
the device it now is gonna be okay, some object, right? Could be a decoder, for example. And let's say it has it's let's say it has like whatever the internal architecture with all the weights and whatnot. Then I think the hidden states. Do we have to? Okay, let's say we are passing CNH. Even though it's going to be the same time all the time. But then we have to pass word 1, word 2.
So I don't think you have to pass 2 words. I think you only have to pass 1 word at a time.
1 word at a time, but how do you know if it's because the way I see it, once you call it, it will construct that decoder and say hardwire these 2 words. And then give you the last word, the 3rd word. And then you take this guy and like, okay, call me like decoder again with this H and C and with these words.
I can't quite read that part. That's like where we are, like our yeah. It's not doing 1 word at a time. It's doing then unigram. Then the second time it's doing bigrams, then trigrams. So it's like at T3, it's taking as input 2 words.
I think if I write it as a Python class, then it's okay.
Yeah. Yeah, because we're constructing the optimal paths. So with word, once we get to word 3, we're selecting the best of 2 word sequences. Word 1 and 2 are selected already.
Well, word 1 and 2 already selected?
Yeah, like we're at time 3 now.
Yeah.
What you are taking as input for the beam search is the best 3 of word 1 plus word 2.
Yeah, like, but William, don't forget that we can have 2 separate models.
Yeah, that's correct. Like, yeah, now you're branching off again.
Yeah.
But you're branching off. Like, so you pick the best 3 word 1s. Now you're going to pick the best 3 of word 1 concatenated with word 2.
Yeah.
So it's bigrams. I don't know if that's because it sounded like if I heard you guys right, whether that was an issue or not.
Bigrams. Yeah, because to me it seems like you want to use the same model and just add the new word query with the new last word. Is that the case?
Not the new last word, like what the beams, like it's the new last. Well, how would you say it? It's because it's constructing a path. Like you're not at time n, you're not looking at what is the best 3 words of time n minus 1 alone, because you've got the history from all the other previous time steps. So you're picking the best 3 paths. Like, so if you're doing that tree search, if like say you're expanding a tree, right?
Yeah.
Start at the root at the top. You got a bunch of branches, M branches coming down. You pick the best 3 of those M branches. You expand those. Each of those have M for the one branch, M for the second branch, M for the third branch. You're picking the best 3 from all of those.
Yes.
So that's including, so that's word 2 and word 1 being included. If you know what I mean, if I'm expressing it properly, it's, well, we get it. That kind of search tree, that's what we're doing.
Yes.
All right.
Yeah, it's the same kind of way I imagine coding it. So when you first instantiate this object, it's just given whatever state is being passed from the encoder.
Mm-hmm.
So we have our H, we have our C set by the state. Then for the first iteration, we run the model, but then the word is just going to be like 0 or something, right? Just whatever the start is.
Mm-hmm.
And that'll output the first set of probabilities.
Right.
But during this predict, either like we update the internal state of the model, because it changes, right? Based on the word and all these gates, whenever you run this,
Mm-hmm.
its state is changing. And then that change in state is kind of like remembering what happened before. Because if you pass it the same word, the same inputs, the state's going to be the same every time. It's not like, it's not probabilistic. So you don't have to pass it like every word each time. Some kind of, they're getting at, there's some sort of H and C that's just maintaining.
Where the only difference is between what I was talking about and what you're talking about, there's only one difference, and that would be taking that Y hat, changing it, the output vector, that Y hat, you're making a selection on it, and you're making 3 selections, picking the best 3. You're creating 3 new vectors from that one Y hat vector. That Y hat vector is in turn based on H vector. So you're putting out H all the time. The only difference is that you're doing 3 different Y hats for your 3 selections, and you're putting that into a new cell. So if your translator was not putting out Y hats and you were just using H's, then you don't, there's no sense in creating different instances of the next LSTM cell.
Yeah.
It's only with those 3 different Y hats, and those are modified Y hats, because the Y hat is basically, it's based directly off of H. It's not really adding it's adding some more information, but not a lot from the, or no, wait, there can be a set of weights between H and Y hat. So, okay, Y hat can be different. Well, I guess that depends on the architecture too. You got freedom to choose.
One LSTM at a time?
Sure.
Can you query one LSTM at a time?
Yeah. But like it would make sense. Like, I mean, you can get into multi-threading and stuff, but
Yeah.
I'm not that good at keras. I don't. That's why to me it sounds confusing. Like, how can you just say, okay, just query me this LSTM right now?
try to
Give
write
me this LSTM.
pseudo code. So
Yeah. So it's different Y hats then, and that's what you're inputting, and that's where you're going to have to then create extra instances of LSTM.
like we walk through it and just get to like where we disagree or like some sort of issue. Like we agree up to this point, like what's happening. Any
Yeah.
question? There's gonna be some sorted thing, and then based on whatever the beam width is, we just call it a for loop. But I think this has to be done recursively. But for candidates in Y1, in this case, it's just going to be like the top 2 candidates or whatever.
Mm-hmm.
We have, you can say like decoder. Yeah, it's got to be a recursive function. You can't even do a loop.
Okay. Yeah, I think I know what you're talking about.
Because like if you said like, okay, for the first candidate, we're gonna run through this model. Or actually, you know what? There's no way we can do it.
I do remember he said that when it came time to like bigrams, so 2-word. So you pick the first 3 best 1 word. Then when it comes to word 2, so it's 3 plus 3 plus 3. So you got, you know, k squared options, right? But you're only picking then that second time, you're picking the best 3 out of those 9.
Mm-hmm.
That's my understanding.
The best 3 like pairs or trigrams, and you calculate those based on all the individual conditional probabilities that you like maintain in your state somewhere.
Yeah.
Where that would be part of like the beam search.
Yeah. So then next iteration, word number 4, you're getting the input of the best of 3 from the last time. Now you're going to get 9 candidates, and you're picking the best of 3 from those 9.
Yeah.
Yeah, and you're doing that each iteration.
I guess the way you could do this is you have to start with some sort of map, like or a dictionary. It always has like whatever the width is, and then we keep updating this dictionary with whatever instance we're going to keep. Now it's too late to go back and change this, but we could say like there's some models. Our dictionary 0 is like, it'll start off with this original decoder. 1 is the original decoder. And then we could do like for I candidates in Y1 and enumerate this, of course. Then we'll say models I is going to be equal to this decoder. Oh shit. So essentially we go for I candidate and whatever this beam with this, in this case is 2. So we have 2 candidates. We'll update this one with the result of running the first candidate. We'll update this guy with the result of running the second candidate. And then after this case, we have to evaluate, well, and then in the beam search part, evaluate the probabilities. And then based on that option, if we find out that the best probabilities are only in the second candidate model, then we replace the first one with the whatever one that survives. If one word comes from here, one word comes from here, this doesn't get touched. If both words are coming from this one, then this gets copied here. That's why we maintain like the memory of the model, how it's decoding.
Mm.
Well, sorry. Well, this is going to be.
You're actually not.
Just,
if I understand you right, you don't have to actually, and I should say it differently too. You don't need different instances kept in parallel of an LSTM cell. It's the same cell. It's just you're keeping track of it, different inputs and the different resultant outputs. Isn't that correct?
Say it again.
Yeah. Do you have a dictionary of, in your dictionary, are those LSTM cells?
These are decoders, decoder objects.
Yeah. Is that the entire decoder or is it one time instance of the LSTM?
The entire decoder. Like it's the decoder, when you initialize it, it's just the decoder before you pass anything to it. It's just whatever weights came from the encoder. and then you initialize the object. And at time step 0, we predict, like, given the start token or 0 or whatever, give us the first probability like vector. I missed the predictor right here.
Yeah, so you're talking your decoder, what it is, it's an LSTM.
Yeah.
So you're talking K number of LSTMs.
Yes.
The thing is you don't need different LSTMs. The only thing that would differentiate one LSTM from another is its internal state, its weights. The only thing I can think of that being a factor is the C.
Well, like that's how.
No, even actually, no, that's not correct either. Even the C, its weights are also. We don't have unique weights, so we only need one LSTM. The only thing that
we need to kind of remember where we started, though, right? Because that's what I think Andrew's getting at by instantiating separate objects.
Yeah, those are just vectors, input-output vectors.
No, like he says, you're gonna want to test like one word, but then when you predict the next word, that model's state has been updated based on that input. And in the other instance, you test it with the other word, its state will be updated by that input, and at the end, they'll have two different states.
Mm-hmm.
That's why you have to maintain like a dictionary of them, so you kind of keep track of what happened in the past. Otherwise, you have to repeat calculations.
Yeah, I think we're talking about the same thing. And correct. Yeah, you don't do that. You're right.
Like in theory, you could keep passing it like another list of words, and at every step, you have to kind of repeat what you did before.
Yeah, correct. Yeah, for me, it's going to be a list of vectors, a list of lists or whatever.
Like that would work, right? But then you're just duplicating computation. Well, I guess you could cache results and you could make that efficient.
Yeah, it's just for me, I'm just appending results.
Yeah, it's two different ways to implement it.
Yeah. Gotcha. Okay. All right then. Then we're on. It sounds like we're on the same page.
What's nice about this, and what Andrew's also getting at, you get fancy with this and like multi-process it, thread it, just crank through everything in parallel. Because it's a beam, like you can do that.
Yeah. If I was to.
So if you have multiple, let's say your beam is 5, you have 5 models, right? So
Yeah.
keep in memory. Okay, and we do that because we want to save memory.
We just want to remember like where we started, like what words were passed before.
Right.
And by using these same models, we don't repeat computations. Because like what you're saying too, if we give it like a list of words, then you have to step through the model.
Yeah.
That many more times every step.
Right. So you have to run through.
It's inefficient, right? But if we maintain it this way, we only ever run through it. We only ever run our model sentence length times whatever the K is.
Right. So this one, I don't think you can query just one LSTM at a time.
Well, it is like it's the one model, but like over
one
time,
cell.
right? Like I'm not. This is like the whole model I'm talking.
Yeah.
This guy's the model itself.
All right. Let me just see if I can split myself better. So we have, this is our decoder, right?
Yeah.
So let's say we have that's. So the way I see, and this one is initial state 0. So that function, from my understanding, is you query this thing, you get your results, then you query this thing, given the outputs, let's say this is our function. Given this function, you query this guy, get some results. The same thing goes here, right? So you query one cell at a time.
No, it's like the way I imagining it. This is LSTM.
Yeah.
I'm supposed to get away at T0. It's the same model now. at T1.
Wait. Same model.
Yeah.
Yeah.
Those are cells.
So this is the way, like when he talks about instantiating new models, it's like you're just querying the model for one output probability. Like it's not cells. It's like the full model itself. Like you keep running the model for a new probability every time, and then within this has a bunch of cells.
No. That's. So when you initiate the decoder,
Remember, this has to be variable, right? How do you control the variable
of what?
length?
Yeah. So you set this one to, let's say, 30. You have 30 cells.
Yeah, this is different though, right? This isn't the.
This is decoder.
Yeah, but like this idea here, you run the whole model because it has to be variable length. You don't know how many times you're gonna run until you get it in the sentence.
Yes, I agree. So the decoder.
I think I just want to step because I think this was the confusion that I got confused with this at first too, with just the diagram, and it's just something easy to forget that LSTM, those 4 squares, it's the same LSTM, that's just at a different time step.
That's the way I understand it now. Yeah.
Yeah, because I got confused with that for a second as well, a while back. But yeah, it's just one LSTM for the decoder.
Oh, I see what you're saying.
I used to think that, and I was so confused, and I was arguing with Xiyang because like I couldn't get it.
Yeah.
But I'm pretty sure like this is the way
It is, and Andrew Ng says that, but he says it really quickly in an early video or something, and
So it
it's
is
easy to forget.
the same LSTM at the different times, right? So all the thing that changes is that C and H, right?
Yeah, it's internal state.
And that's what you mean there, right?
Yeah.
Yeah. And if with the way I was talking about it, I was ignoring a Y hat, and I'm presuming that the information of your selection is kind of in those H's, kind of, sort of, but
yeah,
the way Andrew is talking about it, yeah, no, that Y hat is then added in on top of it, and you're modifying the output because the Y hat is really close to the H, or it can't, unless you have a really messy, dense layer in between.
It definitely contains the same information. It's just one's been.
Yeah, so the only thing that you're changing is that Y hat is you're modifying it by making 3 selections, making 3 new Y hats.
Mm-hmm.
That's our changes. That's our input to the thing, so to speak.
Right. Okay, I think I see the logic here now. I'm still a bit confused with the keeping each model as a separate list, because like my approach would be very inefficient. I agree, it wouldn't be as efficient, right? But it would be a bit easier to follow, right? So let's say you have one model like a decoder. This guy, I don't know these cells or whatnot. And every time, and let's say you have a list. Let's say your beam search is in list. You have 3 of them. I'm gonna make the mess number easier. So yeah, every time you query it, essentially, you say, okay, here's my model. Here's the word that I have. Give me the probabilities for like the second cell. Right. Coder. I'm not even passing C's, maybe very initial C's. But maybe already have C and H. And then just a list of words. And then maybe based on this, like it says, okay, there's only 2 words. I'm gonna run it twice and I'm gonna give you this probabilities out. You take the max out of those, but then you have to, then you don't even have to worry about keeping track of which word were before. Because every time you're running it, there was like A, September, J, right? And then you just append the max word out of all of those.
Yeah, the issue with this, if you use caching, this is fine. So the problem is on the next step, now you have to pass a vector of 3 words.
Yeah.
And you're going to run through the model again, right?
Yeah.
3 times.
Yeah.
So you repeat computations, but if you cache the results,
yeah,
then this will be just as fast.
Cache the results, yeah.
Because then when it sees, okay, I'm running decoder for word 1, oh, that's already in my cache. Like at least recently used cache, it'll just pull that number from memory. You're fine. So it all depends on how you want to think about it.
Right, right.
But if you don't use a cache, this will be slow. That's the only problem.
I see. So if we have like really, really long decoders, really long sentences, like a million words, I think this would be better.
But I think because if you have 10 words, you're gonna have to run through the model. There's a Newton's equation, n times n plus 1 over 2. You have to go 1 plus 2 plus 3 plus 4 plus 5 like times you have to run this model.
Right.
With this guy, you just run it one time and you just save
One
it
at a
state.
time. And save states. Okay, I see what you're saying.
That is the formula, right? N times n plus 1.
Oh wait, you mean the sum from
Yeah, 55.
integers?
Yeah, so the sum of like 1 to 10 is 55.
Yeah. N times n plus 1 divided by 2.
That's what you'll end up doing in this case.
Mm-hmm.
Times k. So your k times n plus 1 over 2. You're looking at n squared. Where this guy here is going to be n.
Okay.
But like I said, time complexity gets solved if you use caching. But like in general, you want to avoid caching if there's like a better, like if you can think of a better algorithm. But it all depends because if you can conceptualize them better, like you can understand it, then go with that.
Yeah, my only concern is when you do this, right? Do you? Oh yeah, you don't worry about the models, the previous version of model.
No, this one you don't have to save your state.
You don't have to worry about how did you get to this state or that state.
No, you'll get there every time.
Yeah, the same. Okay, that part is a bit easier, but I think this one you have to do some housekeeping.
This is an object-oriented approach.
Which models you do?
This will be object-oriented. That one, I believe, you could just do that purely functional.
Brute force.
Because you don't need a state. Well, you just maintain a cache. That's it.
Just abuse it. Yo, do the work.
Yeah.
Yeah. Okay. We'll see. Do you have questions, Louis?
Not too much. I'm just figuring it out because we know what we're doing. I know what the change needs to be made, and I don't know if you can see it there.
Where?
That's where for this particular code case, we want to do the beam search in this loop here. And that's what I'm going to be doing then right after. That's what I'm going to do this later on. I know that. So this is going through the decoder one time step at a time. There's the attention layer is being done. So now for each beam, for each one from 1 to k, you're doing one run through the LSTM cell.
Oh, Willie, sorry. What is that? I think in this case, where does attention go?
Attention it's one attention context vector applies for that time step. So when you're running through the LSTM,
yeah,
k number of times for that time step, you are still using the same context vector.
Okay, so attention is inside of that thing, right? Yeah, remember last time we drew the attention part, it was like too confusing.
Yeah.
I'm still not 100% on attention.
Yeah. Okay, then whatever. I'm just not sure how we're gonna cache the attention vectors here.
Yeah.
Is attention essentially just another state of the decoder?
Yes, it's another vector that's being concatenated on to the okay, yes. Put it this way. The easiest way to say it, it's another input.
Right.
It's another input into the LSTM cell.
Based on the prior history of the last state times this linear combination. Yeah, this is where I get confused. Like I don't
Yeah, it was the entire decoder, all of its hidden states, all of them are used in calculating the context at once. That's why the decoder has to be finished, gone through completely in order and you keep a record of all those. That's, if you can see my screen, that's the A's here. That's all of the hidden states from the encoder, and then one S that is from the last time the decoder LSTM was run. It only gets one hidden state from the decoder, and it takes all the hidden states from the encoder and then does the calculation, the mathematical calculations. It runs it through a dense layer, runs it through weights, and then does whatever else. I forget. There's 3 steps.
So yeah, then that A is just never changing. It just gets updated each time based on.
There's one unique context vector for each iteration of the decoder.
Yeah.
So for word 1 of the decoder, it has its unique context vector. For word 2 of the decoder, it has its own context vector.
Essentially, that context vector is going to tell us where we should look given our
input.
Yeah. As a high level way of what is it trying to do?
Yeah, it's trying to say which words from the decoder or from the encoder, which different words in its entire sequence matter more. Mm-hmm. They're each given a different weighting. And then for some reason, the hidden state from the last decoder step is also included in there. That I'm not sure why. I wonder if that was just a hack job, because including all the hidden states from the decoder or encoder, makes sense, because that's what you want. That's what context is. What's the context of the input sentence? The different words in there. Which one matters more for this particular selection here, for this new say for a translated word? That makes sense for the context. So yeah, I don't get why the S is thrown in there as well, but it is. So anyways, yeah, if you're seeing the screen, it's for time step, the one unique context vector, and then now we're going to do K runs through the LSTM to get the K different results. And so we need the K unique inputs, and then the K unique, and then, oh, just wait, there's K unique inputs. Hold on a sec. Yeah, no, yeah, hold on. Okay, we need K runs in, and then we got to make the selection. So yeah, code is going to go here for selection. All right. Okay, hold on. All right, I'm not thinking right now exactly. I'd have to think through it. So anyways, this is the way I'll be doing it for this. I'm going to try this toy problem, get it right first.
Yeah.
So are you going to be using this, or are you going to try something else?
I was going to continue with the language translation.
Oh, you've been running that?
Yeah, well, I was doing the work all the pre-work to process and do all that stuff. I'm trying to learn the full thing.
All right.
Did you do the word embedding?
I'm at that step.
I see.
Yeah, I didn't get any work done on it this week.
Okay. I was trying to use the word embedding, and I was trying to use glove, but for English it's easy. You can just, I'm going to show you actually.
Yeah, I'm going to test both results, doing our own word embedding based on data set, which I imagine would lead to overfitting. and then but then the interesting part is I think it'd be better if you're trying to make a thing that samples, like if you want to make an RNN that generates something that's very close to its source, then making a word embedding out of the source is the way to go. But if you want a general purpose translator, then it's better to use one of these pre-made ones.
Yeah, I want to use this pre-made one because it's kind of for every single word it gives you the
Oh, nice.
dictionary, right? I mean the vectors.
Yeah.
So this is whatever you can download from their official website. But this one is available in English. It's not available in other languages. That sucks. You can generate it yourself, but that's what I would have to do manually. I was just hoping that someone's built it already.
There really is none for any other language.
I mean, I found one, but it's not Glove, and maybe it is Glove. I just found one. I mean, the game, like 2 gig, 2.3 gig. Oh, what could be in there? Because English, because the English one, the 300 dimension is like just 1 gig.
How many dimensions was the other one?
I don't know. I couldn't open it. It's too big.
Oh, Notepad won't even do it.
Too big for.
Oh, you know what you can do? Do you have Python?
Yeah.
Here, I'll send you a code. You can read the file. I just have a simple recipe for streaming. That's what I was...
Which data sets are you guys talking about? Is it the one that's on the Google Drive, the English German, or are you trying something else?
Oh, I found the code online. I'll see if I can. Okay, so here's the link. It's on RNN channel. So it's a German word embedding. If you scroll down, trained embeddings, German Wikipedia.
Yeah, I'm looking at it now.
Yeah.
Pre-trained in Dockerized Glove, Word2Vec, and Fast Text. So yeah, Dockerized, well, it could be nice. It's Dockerized, not straightforward. Oh, just wait, is it all trained models?
Yes, trained embeddings.
Oh. Does it include the data sets? Are you grabbing from there? Trained embeddings, vectors, and vocab.
Yeah, I'm just getting the vectors. The vocab.
Did you get it open?
Eurocode?
Or sorry, which one? You found another one?
No, this one is the vocabulary.
Okay, vector text, 2 gigabytes for Glove. And then Word2Vec. Vectors. Refresh. Do you guys know what Glove is?
Yeah.
Okay.
Glove is another way to do Word2Vec.
All right.
Right? Oh, sorry, that's what I have to go over.
Yeah, and these vectors are the word embedding, right? All right. I see the code here, Austin. So what's this? Chunker, file chunker?
It's just a way to stream any kind of data.
How do I read this? Do I use chunker or?
So use file chunker and just give it the name of the file. Give it a chunk size, which is by line, and then n amount of chunks if you want. But if you don't give n chunks, it'll run through the whole file. But it's lazy evaluations. You can see it like one line at a time.
What should be the chunk size?
You can give it 10. Never many lines you want to read as a 10.
Number of chunks, just ignore it, right?
Yeah. That's if you only want to grab like half the file, then you do that.
A way to read through like a 2 gigabyte file, right? Without.
So give it next test. The Python special.
Yeah.
And this is handy. It's doing a stream. Or like brackets. Or parentheses.
It is.
Run that. I got importer tools. This is a very handy recipe for streaming data.
Yeah, good. Thanks.
That chunker has worked for any iterable. The file chunker is just to make it work for files.
Yeah.
You have to run this again.
It goes through everything. All right.
Oh, sorry. The yield's in the wrong spot. Sorry, the tab got messed up when I copy pasted it. Put the yield within the for line and lines.
Here.
Yeah, indented again.
Here.
Yeah, that's it.
All right.
You should get 10 lines every time.
Okay. Oh.
Every time you run that, you'll get a different result. Like it's stop iteration.
Is it a list?
Yield line's only supposed to be indented once.
Sorry, it's supposed to be indented twice. Yeah, when I copy pasted, it got messed up. I'm gonna edit my comment here.
And for some reason, my editor is putting it with the if. 1, 2, 3. It's putting it in 3 times for some reason.
Okay, so it's 300 dimension for each word. But why it's 3 gig? German's bigger than English.
Is this the glove?
Yeah, yeah.
Yeah, it's possible. It's just like way more words.
Maybe they didn't tokenize it.
Not sure.
Yeah. Oh well. Because yeah, I don't want to use the decoder. I don't want decoder dictionary to be greater than encoder dictionary.
Well, if I remember, there was 2 dictionary sizes. I think source had a larger dictionary.
Yeah.
And this guy's paper. Yeah, 160,000 for the source language and 80,000 for the target. And I'm not sure why it's different. I just noticed with Spanish, you ended up with a way bigger vocabulary for the data set. I think because it's just way more conjugations.
Yeah, that's what I was thinking. Maybe same thing.
I don't know anything about German. It might be the same case.
Yeah, I think they just failed to tokenize it, and every single like simple word is there.
So in this case, if you make this one, you can just read like one word at a time.
Hey, nice. Perfect. I'll save this guy.
It's very handy.
It is 300, yeah. All right. So maybe then the German to English.
Yeah. Yeah, like whatever to English was the way they originally did it.
If you find some other, I don't want to train my own word embedding vector. That's the other reason. I did it once. I'm like, okay, I know how it works.
I've never done it, so I'm gonna do it, and then I'm gonna test the results and show that how much better it is to use like a pre-train.
I see. Yeah. I think there's just download the code from Stanford from the official page. It's very easy. Just bash it once and that's it.
I couldn't figure that out. I tried. It's from someone posted it, right?
What are we talking?
Talking about glove word embedding. We're talking
Stanford glove word embedding.
At this page.
Okay, you got it.
Oh,
All right.
I never tried this.
So we'll download the code.
Getting started. Code download. Pre-trained word vectors. All right, hold on.
Yeah, and then you just need to modify this demo. Well, I think that's what I did last time.
Yeah. Extract here.
So yeah, what it does is essentially you download the. Oh, okay, let me share my screen so you can see it. Can you see it?
Yep.
All right. So essentially, what it does is it downloads the corpus of some text.
Bash
Uh,
script, yeah.
yeah. Then it creates the vocabulary text file, and all this is just a setting, so format.
Yeah.
Then it builds the vocabulary, essentially. So it goes through your corpus, and then it's I'm not sure if it does if it tokenizes it, but then it every single unique word it puts it together, and I think it sorts it by frequency, the occurrence. So and then you have your vocabulary, and in your vocabulary text you have the vocabulary and like its index essentially.
Mhm.
And then once you have that thing, it will run through Glow file. Then it will do the word embedding thing, and it will save it. I forget what is the name for it. Do you pass the name for it? Maybe you pass it yourself. But yeah. Oh yeah, vectors. It will call vectors. Then it will save the vectors with the word, and then all the dimensions for it. That's it. And then you just use that as the output. You'll get something like oh, get something like that. Yeah, you gotta open up the readme, I guess. Yeah. So you just run the bash command. Just modify the demo sh to point it towards your thing because you don't have to download anything.
Right.
So, you know,
I thought that was whatever master structure.
yeah,
And I'm guessing it's just lines. I'd imagine it's the same thing. Right? One
Yeah.
line, one line, one line.
Yeah.
Per sentence. Cool.
Corpus text 8, essentially this guy. So you just put your own thing.
Okay.
The
And
previous.
it wants a zip file. Okay.
No, you don't have to have a zip file. It unzips it.
Oh, it unzips it.
Yeah.
Oh, I can just get rid of that line.
To give you your own text. I'm not sure if you could just pass txt file.
I can probably just do that. I change this parameter to whatever my text file is.
Vocabulary?
Yeah, and just comment that over.
No. Vocabulary
Oh, sorry, that's
is
vocab.
created based on your corpus. So once you have your corpus of text,
Yeah.
you save it. I don't know.
Where is the source? Like, how does it know which file to grab?
It will grab it. Scroll up. It will grab corpus by default.
Oh, text date.
It will come from it.
Okay.
Now this is demo. Try to run demo once and then. Run
All
it
right.
out.
So yeah, I have to just change this name to whatever my file is.
Yeah. And then the rest it should do it.
I gotta learn Bash.
Hmm?
I have to learn Bash.
Yeah, same with me. I'm not too crazy about Bash. I mean, I can hack it. I can understand what's happening in
Yeah.
it, but I cannot like.
It gets
Right,
really
right.
annoying with these like dollar signs. And
Yeah, it's pretty ugly and or unintuitive, right?
Yeah, first like get confused with all the dashes. Like when they say like dash D, supposed to mean dash. It's a data. Dash N when it's like you do this or you do that, and then like dash E. Okay, what do you want me to do here?
yeah, I have no idea what that means.
Or like dash O. What do you mean by that? So each one of these has like some
They're
meaning
optional
behind it.
arguments.
Yeah, but like by
You have
the
to
time you
learn it.
go there,
Like if you do if I do curl dot h dash h,
it's a hitter.
then you can see like what each of those guys is gonna do.
Yeah,
So I guess O does
just pain. I don't know.
yeah.
It's too many.
I don't have these on memorized.
to memorize all the stuff. I agree.
Yeah, it's pretty ugly.
Oh, it says O is a write the file instead of standard output.
There's capital O and there's lowercase.
Yeah.
What it is that you guys are trying to do here?
This
What-
This is essentially word embedding. Like in our current code, we input the one hot encoding, right?
Yeah.
So this is another way to input the words, because you know the vocabulary, like English, for example, it's more complicated.
Yeah, but what are you? Yeah, sure.
I did
But
all.
for this, you want to mod the script. What is it you want to?
So
What are you
let's say
aiming
you
for
want
here?
to let's say you want to do one hot encoding in the English vocabulary, right?
Yeah,
One of your vectors is going to be 8,000 long. That would be the size of your vector for each word, 8,000
yeah.
zeros, and one of them is going to be one, right? In this case, each word is represented by 300 with a vector with the length of 300 instead of 80,000. So it's just more compact way of representing a vocabulary.
All right.
Yeah, and this one essentially, what it does is it's shows the distance of a word compared to other words in 300 dimension space. So it captures the relationship of those words.
All right. That's the embedding size is 300.
Yes, yes, 300 dimensions essentially.
Yeah.
And there's like other, you can, with the glove, you can say, okay, I want my output to be 300 dimensions, or you can say, I want my vector to be 50, 150, and so on, and it'll do it for you.
Right. And so this thing here that we downloaded, this looks like, so this is code for to modify, to get the data set and to modify it.
So whatever I'm showing now is official code from the creators of glove algorithm.
Yep.
So what it does is it actually goes through your corpus of text, creates the vocabulary based on that, and then creates the mapping like this word to vec.
This is doing a lot of the workload because it's going from the raw corpus, right?
Yeah.
Yeah, I wrote all of this in Python.
And I'm like, damn.
Oh yeah. Yeah, I saw it that they are using C here for it, right?
Yeah, they use C. They use C sharp.
Glove, concur, vocab count. Here's glove C.
Listen, you wrote this thing yourself?
Yeah, but I wrote also code to translate the corpus as well to integers. I did like it's a bit more, but that first step is the idea. What I had to do first is take the corpus, get a count of all the words.
Yeah.
So then you can pick what your vocabulary size is.
Yeah.
And then map it to integers. That's basically like what I did.
Right. Okay.
And then translate the text.
By translate, what do you mean by translate?
Take the words and translate them to their integers. And then that's what it'll actually be like. Because then you're going to go from integers to the embeddings.
Oh.
It's just like it's the way I've just seen it done.
Yeah, translate from. Okay, got it.
Every word gets its unique index number. Essentially, that's what you're talking about, right? Yeah.
Yeah, and then essentially what he's doing, he's going back through his corpus and replaces every single word by its integer.
And then it gets fed. You can feed it to the model.
Yeah. Okay, got it.
Yeah.
I just wanted to do it all by hand just to kind of get an understanding.
Yeah, good. Yeah.
And I like the code. It's my job. I gotta get good at it.
Yeah. Well, that's how we get good at this. That's how we learn, right?
If you guys get really good at code, like at coding, then maybe you can build some of those models.
Yeah.
For the platform.
Yeah.
Here's the interesting thing. Okay. I guess I'll say that. A lot of researchers, they publish their papers, but they're horrible coders.
Yeah.
They cannot code for life, right? So what they need is a programmers. So essentially for our platform, we'll have researchers, and if they cannot code their thing into a proper format, like we'll say, okay, we can put your idea into code so we can serve it properly.
Yeah.
But then you're gonna have to split the profit with whoever coded that.
Yeah, that's the way it's how it goes, right? Like it's hard to be good at everything.
Yeah.
It's just more efficient. Energy.
So if you guys are interested in coding, let me know. I'll look at some models.
Hey, great. Yeah. Hey, I'm ambitious. I'm hoping to be able to hit it both. Do good code and do good research.
Yeah.
That'd be nice.
All right, so it's already time. Let's wrap this thing. Do you want to discuss anything else, or are we good?
I think we're good. And if anything comes up, we can always message on Slack.
Yeah.
Yeah. I can't think of anything right now.
What's any questions?
Oh, I'm good.
I think we'll be like, let's try to do. I'll try to do the translation because I'm more interested in the glove part. I'll try to run this with the word embedding part. The beam search, I'm not that crazy about it yet. If I have time, I'll do something with it. But
I might try to do the beam search this weekend.
Yeah. All right.
Well, no, well, I need a model first before I bother beam search. So I'm just gonna do word embedding things.
Yeah.
Yeah.
As long as I can do work. If you manage to do this glove in German, yeah, let's say 50 dimension, right? You can just upload it. Share with us. So I'll just reuse that instead of reinventing the wheel.
What is it you're going to try and do? You're not going to try and do. Are you going to just use somebody else's code for the model and just try and get the data all set up and everything and see if it works?
The model you ask me?
Or either of you guys, Austin or you, are you guys? Because it sounds like you're doing something ambitious by trying to do this big data set. So, are you guys going to try? Each of you going to try and still, code from scratch?
No, so I'm not that ambitious. So what I'll try to do, we already have the one with attention. So I just modify it a bit. So it accepts as an input my word embeddings instead of one hot encoders, and then just train it on some simple English to German data set. And for that, you just need to have that word embeddings in proper formatting, like glove or word to vec or whatnot.
Right, got it. Okay.
I just want to reuse someone's embedding, and Austin wants to write.
Well, the embedding, if I have words, I should be able to get their vectors, right? Like, there's already like a defined
dictionary?
Yeah.
No, you need to have actually.
So it trains the model.
It trains the models based on sentences, because you want to know what they are. It's not just the.
So it's not a pre. I was under the assumption it's like a pre-trained embedding.
No,
and we're just processing the file to figure out what vocab we're gonna get.
No, if you go through the glove paper, they actually explain. They make a matrix of occurrences. How often does this word occurs with this combination of these words?
Yeah.
Based on that, it constructs the mapping. So
Oh yeah, no, I won't try to. I can do the pre-processing, but I won't try to invent my own algorithm.
So yeah, just use whatever they gave you. Like the only thing you might have to watch out for is tokenizing it. I think these guys that made the German dictionary, they didn't tokenize their corpus.
Yeah.
So that's why it's.
I had to do some data cleaning too on that, like that raw data set, and to tokenize it properly.
So maybe it would be easier to find some language that uses only English vocabulary, without this fancy like dots and whatnot.
Oh, diacritics, yeah. Well, there is a way to clean those with the Unicode standard library.
All right.
I have it in my Python book. It's called Unicode normalization.
Oh, nice.
And Google does that too. Like they don't really pay attention to the accent.
Could you share that thing, like the name for it?
Yeah.
So we can solve it. All right.
I have it from my book, but there's probably a good tutorial online. There's basically two. There's like it comes down to how aggressive you want to be with it. NFC.
All right, Will, we're gonna wrap up here.
Yep. All right, sounds good.
All right, man. Thanks for joining.
Yeah. Well, yeah, for sure. Thanks for doing it again.
See you next week.
Yep. All right, take care.
Bye.
Yeah.
See ya.